Good afternoon, friends. So today our session is remote sensing and GIS applications in geological studies. And I am R.S. Chatterjee. I'm from Geosciences Department, the Indian Institute of Remote Sensing. So to begin with, although you know what is remote sensing and what are the applications in geosciences. So remote sensing is the science of seeing Earth, nowadays planetary as well, planetary objects from a remote distance without coming in contact with the object. But what is important, it is using electromagnetic radiation that is received from the objects, either by the process of reflection or by radiation, or as well as backscattering. It happens in case of microwave radar remote sensing. So now let us see what are the applications. You see, there are certain basic applications, and there are many these focused and actual applications we have in geosciences. The basic applications are, first is geomorphological mapping. You know geomorphology, we'll discuss in the subsequent slides. Then lithological mapping, that is the rock types, mapping of the rock types in the earth crust. And geological structure mapping, that is the mapping of the geological structures, means the structures developed due to deformation, due to tectonics. Okay. Now coming to the actual applications, very focused applications like mineral exploration, hydrocarbon exploration like your oil, natural gas, even coal. Then groundwater studies like groundwater prospecting, then groundwater quality, then groundwater aquifer compaction modeling or groundwater flow modeling. Okay, there are many related to groundwater. Then construction material exploration, limestone, like granites, okay, like marbles, different kinds of stones. Okay, these are very, very important, and they are used as construction material. Then engineering geological investigations. So this is related to engineering projects, okay, like this your hydropower projects, okay, like the tunnels, like the highways, particularly in the mountainous terrain, okay, and then environmental impact assessment or EIA. EIA may be of these engineering projects like hydropower projects, the mining, many others. These areas. What are the environmental impact? So that we can do using remote sensing and GIS. And geological hazards, it is very important. Like natural hazards, there are many kinds of natural hazards. Okay, like your hydrometeorological hazards like flood. Then there are climatological or environmental hazards like forest fire, like drought. Okay. Similarly, geological hazards like landslides, earthquakes, and many more. We'll discuss in detail. But see, remote sensing is more effective, more powerful when we work remote sensing data uh, as a complementary this thing, your information with many other ancillary data like geophysical data, like geochemical data, and subsurface geological information sometimes when it is available, not always it is available, and most importantly, ground truths. But ground truths, it is only selective. So you need to find out the areas, so sampling points, okay, accordingly you have to collect the ground truths. Now, say remote sensing, it is done by the satellite, by the aircraft, or nowadays by the drone, even by this terrestrial, this remote sensing by the camera from a distance. But in all the cases, we take the image from above the Earth's surface. And when you take an image, then it gives you information about many things about this about the Earth's surface, like topographic information. Topographic undulations will give you the shadow effect, the vegetation cover, depending on the vegetation type, vegetation density, then land use and infrastructure information, then soil information. Okay. Along with that, there are geomorphological information, then lithological, rock type related information, and geological structures. Now, while we are going for geological applications, then it is our job to separate out this information like geomorphology, lithology, and geological structure from the image. The same image can be used for different purposes. It can be used for vegetation. This information can be used for land use, infrastructure, from soil, agriculture. But as a geologist, this is our job to separate out this information related to geosciences, maybe directly and sometimes indirectly, depending on when the information is available, when it is exposed to the surface. Okay, very easy to interpret. And how we do that? We do it by visual image interpretation or by digital image enhancement, okay, by logical reasoning, and followed by feature extraction. See, here for this interpretation of the geological features, there are certain direct interpretation keys, direct interpretation elements, okay, like what is the color of the object or what is the stone in case of black and white image, then the texture, the frequency of tonal change, okay, then the shape or form of the object, size of the object, then the pattern, and then association. They are the direct interpretation keys. And there are indirect interpretation keys like the landform, like what is the drainage. Drainage it includes many things, like what is the drainage, this your longitudinal pattern, what is the cross profile, what is the drainage anomaly, what is the drainage density, isn't it? These are many things are there in related to drainage. Then vegetation, what is the vegetation cover, vegetation density, and finally land use. So these are the indirect interpretation keys. All the things are given here. For example, you can see that there is a tonal difference at different parts of the image, isn't it? Here you see the textural difference. Here the texture is smooth. Here it is coarse. Here there are some pattern is there, isn't it? And here you see that there are some unique shape of the object. Okay, these are the oxbow lakes. Then you see the pattern here, alternate dark and bright. Here you see this your crisscross pattern, and here you see the association. So when we these cones we see, then the other things are very, very clear to us. This is what is the this beauty of association, isn't it? So this the white lines, it represents the lava flow lines. We can interpret it very easily when we know these are the volcanic cones. Now landform, we can see here the landform, there are ridge, then valley, there are some triangular facets, isn't it? There are some dissections by the streams, isn't it? You can see all those things. The sandstone and shale, sandstone and shale, sandstone and shale. In the sedimentary rocks, it develops this kind of your landforms. Then you see here drainage. See, it looks like a tree that is known as dendritic drainage pattern, isn't it? So that tells you about the geology. There is no structural control, there is no tectonics, and what it may be either these massive igneous rocks, or if it is a sedimentary rock, it is also possible. But in such cases, the sedimentary rocks should be horizontally bedded, no dip of the sedimentary beds, isn't it? Now you see here vegetation. Vegetation has a particular pattern, isn't it? That tells you that, and this pattern also shows you there is a pattern of the drainage also, isn't it? So that gives you the information about what are the rocks are aligned. Homoclinal beds are there, isn't it? Here you see this the land use. See from the land use here, all the settlements are here, habitation. And what is the shape of this habitation? Like a fan. And this is basically alluvial fan over which the habitation has been formed. Habitation has developed, and this is nothing but this Panchkula, okay, the near Chandigarh area, Panchkula fan, and this habitation from the land use we can interpret. Now coming to this interpretation of rock types, this is one of the basic information what we can derive from remote sensing images. See, this is one of the samples, very this important sample. Sorry. Here you can find all three kinds of rocks, like you have igneous rocks, you have sedimentary rocks, and metamorphic rocks in the same area. So in this sample, you have all three kinds of rocks. Now you see what are the characteristics of igneous rocks and how it will appear on the image. So a characteristic you see, igneous rocks, they are homogeneous because they are crystalline rocks. Okay, from the melt, they crystallized, they are interlocked. So that is why they are very hard and compact, they are massive. Okay, and in general, there is no bedding unless the igneous rocks, when it is extrusive, like a lava flows or traps. In such cases, you will find some kind of layering. Otherwise, there is no layering and there is no bedding anyway, isn't it? And because of these properties, it usually shows coarse textures. And there is the very characteristic joint patterns, orthogonal joint patterns or radial joint patterns and landforms. So from this, we can interpret where this coarse texture we find the massive appearance in this area. So this is the igneous rocks, and this is light tone. So we can say this is the granitic shoot of igneous rocks. Okay. So this is not fine grained rocks, but it is a coarse grained, so plutonic igneous rocks and granitic family igneous rocks. Now sedimentary rocks, you see, what are the characteristics? They are soft and bedded. Okay, because they are soft. Why they are soft? Because they are deposited rocks. Grains are just lying side by side, so they can be easily eroded, so vulnerable to dissection. As a result, their texture is very fine. They are smooth in appearance. There are many drainage, and because of the differential resistance to weathering erosion, because they are layered, some layers are hard and some layers are soft, and because of that, there will be this ridge valley topography. Okay, some layered appearance is very, very prominent. You can see here layered appearance. The surface is very smooth, fine texture, and there are a lot of drainage, isn't it? So this is the sedimentary rocks. Now, in case of metamorphic rocks, what are the characteristics? Metamorphic rocks, they are formed due to the higher temperature and pressure. So pressure means there are some compression or extension. So because of this, your pressure, there are the regional foliation planes developed. And because of this pressure, there can be folds, or lineaments can be developed, depending on the nature of the stress. Okay. So this regional foliation, it will give you striated appearance in the rock mass, okay, due to the differential weathering along the weak foliation planes. So you see here, this kind of striations, you can see here. So this is the area represents the metamorphic rock. And most importantly, you can find deformational structures, many areas, not always. In metamorphic rocks, you can also find the deformational structures like folds, faults, isn't it? Lineaments. Okay, that we'll see in the next slide. See here, what are these rocks? They are the extrusive igneous rocks, isn't it? The volcanic, these cones, this is the lava, pyroclastics, isn't it? Similarly, there is this volcanic flow, isn't it? So you can see there is the dikes here, and these are the host rocks. Now you see here, this is the granitic, these rocks, intrusive rocks. Whereas here you see, there are these weak planes has developed. There are many. So these regional foliation planes and this your joint planes are well developed. So this is not igneous, but it is a metamorphic rock. But here you see, these are also metamorphic rocks, where deformational structures like folds are very, very prominent. Now in these two samples, what are they? All of you can tell now. These are sedimentary rocks, isn't it? Because you see, there are very smooth appearance, the surface, lot of drainage, isn't it? And their layers are very, very prominent. Differential weathering and erosion. One layer is hard relatively, another layer is soft. So ridge, valley developed, isn't it? Here also you can see a lot of drainage, a similar kind of appearance. Now coming to the next, this kind of information, what we can derive from remote sensing images, that is geomorphology, isn't it? And what is geomorphology? Geomorphology is what? Geo, morpho, and logy. So it is the science of the earth shape. No, science of the earth surface shape. So it is the science of the earth surface shape. So how we can define earth surface shape? We can define earth surface shape as a function of elevation, slope, and surface ruggedness, surface undulations. That means rate of change of slope. Slope is rate of change of elevation, and surface ruggedness, rate of change of slope or slope shape. Okay. So geomorphology deals with the physical processes and the materials involved in shaping the earth surface. And you see, in geomorphology, the basic unit of geomorphology is landform. And landform, how we define? It is characterized by its unique topography. So for a particular area, the topography is very unique, and the material composition, I mean your material grain size, so material composition and structure is also within a particular range. It's not varied. Sometimes it can be varied also. Sometimes particle size will be very, very this your narrow range. It depends on the what are the geomorphic processes are involved. Now you see geomorphological this your provinces or geomorphological classes are broadly divided into two types. One is exogenetic and another is endogenetic. Exogenetic means it is developed due to the force of gravity, externally developed, and endogenetic, where the force involved for these geomorphic processes is coming from inside the earth. What kind of forces are coming from inside the earth? Tectonics, isn't it? Tectonics and volcanism. These are the forces are coming from inside the earth. Now you see in geomorphology, we can study what are the shape, broadly the morphography. We can measure this your size of the landforms, their shape, characteristics, morphometry, then when they have formed morphogenesis, and if there are different kind of landforms, then what is this temporal ordering, morphochronology, and finally what are the presently operating these geomorphic processes? What is the present geomorphic processes or morphodynamics of landforms? Now, as a layman, how will understand geomorphology? Geomorphology is basically it is this your definition of the earth surface shape in terms of elevation first. So highland, plain, and valley. Now, after highland means high elevation. Then what are the slope characteristics? Whether the slope is changing frequently or slope remains this your same. Like in case of plateau, elevation remains constant for a big area, and on the plateau fringes, suddenly there is the steep slope we find. But in case of hills, very quickly, very frequently, this your elevation is changing. Okay. Then in case of plains, then we have pluvial plain, aeolian plain, coastal plain, as well as due to tectonic processes, we can also have certain kind of plains, like pluvial terraces. Now valleys, like river valley, glacial valley, and also by tectonics like fault valley. Here, this we have already discussed. That is this alluvial fan of the Ghaggar River modified by human activity. This is the Panchkula city near Chandigarh. Now see some other areas, like this is one from the northeast. Okay, you can see here these fluvial landforms. This is fluvial geomorphology. You can see this is broadly the alluvial plain, isn't it? This is the active flood plain. Now see, this is the sandbar. You can see this is the natural levees, and some are the paleo-natural levees, and these are the oxbow lakes. Again, you can see here the different level of river terraces in Dakpathar area. What you see here, anomalous drainage that represents some subsurface structures. Here you see this is also fluvial landforms. You see here the meander scar. In fact, it is crawling, meander scroll, and here you see the abundant channels, and here you see the paleo channel belt. It's from Lucknow and Kanpur. In between that, there is a wide paleo channel belt. Okay. Now, finally, this basic information, what we can derive is geological structures. What are geological structures? Like folds, like faults, lineaments. Lineaments means joints or fractures, and unconformities. And you see, remote sensing is very, very important for mapping or interpreting geological structures. Why? Because if the structures are exposed, we can get the synoptic view of the structures. We can see the structures in totality. For example, this is an exposed fold. We can see this entire fold. What are the geometry of the folds? How this folded bed is dipping? How this curvature is? What is this approximate plunge? This direction? What are the geometry of the fold? We can see. So only selective ground truth can help us to interpret the structures. Just to have what is the deep at that particular point, what is the deep particular point. But other than this, the folded geometry is clear to us. But when these structures are not exposed, buried structures, in such cases, we should use the indirect signatures, like what is the topographic anomaly, subtle topographic high is there or not, or drainage anomaly, whether there is a circular anomaly, whether drainage is having some turn, isn't it? Whether this drainage diversion is there, parallel drainage diversion. So these are some indicators of your subsurface folds. Similarly, geological faults and lineaments, they can be identified from this linear physiographic. Here see physiographic, this features, linear physiographic features, and or tonal signatures. Sometimes due to soil infilling, we get the tonal signatures also, or vegetation growth. If there is displacement, then it is a fault. Otherwise, there are the fractures or joints when there is no displacement. So geomorphic signatures such as topographic break, drainage segment anomaly, stream migration, they are some of the very, very important indicators. Like here you see, the entire Sibalik has been displaced. And here what is the river? The Yamuna river is flowing. So that means here is a fault. This is strikes the fault. This is a Yamuna tier. Okay. The thrust sheet. Okay. This is the MBT, isn't it? So thrust sheet. Sorry, this is the HFT, Himalayan frontal thrust. Okay, because between the Shivalik and the Indo-Gangetic plain. Okay, so that is offset by this Yamuna tier fault. Similarly, here you can see fault. You can see the fractures and you can see the joints. Joints because they have the regular pattern. So after these optical images, we can understand well. Then we will use some other your areas of electromagnetic spectrum. So here you see some of the examples of the geological structures. Like you see here the symmetrical repetition of beds. Isn't it? Here there is the Bocable shell, then the Tipom sandstone, then the Woburn sandstone. There are characteristic. These all are very, very unique. Here there is the shell at the center. So there is the depressed zone, alternating sandstone shell, Tipom, and the massive sandstone. This is the Woburn. And here you see you have a closure, you can see. So here, what kind of fold it is? There the folded beds are dipping towards each other. So this is the non-plunging syncline or non-plunging synform. Whereas here there is a closure you see here, and the folded beds dipping away from each other. So plunging anticline or plunging antiform. Now you see here, can you see some peculiar pattern of the river? Rectilinear, straight. And soil infilling you see all along this line. That is the reason why we find this tonal anomaly. And you see the vegetation cover showing a curvature. Actually, this is like this. So there is a fault, tractile shear plane, which is passing through this. Okay, and the river is flowing straight because of this fault. Okay, this we have already explained. So this is the faults and fractures and the joints. Here there is a thrust and there is a fault here. How we interpret? For that purpose, we need to we need to map the form lines or trend lines of the beds. So after we map these trend lines or form lines, then we after seeing their displacement is there or not, we can map their fault. So now after this, to some extent, understanding how optical images needs to be interpreted in terms of the rock types, okay, broad rock types, not the very very particular type of rock types. For that purpose, we have different techniques. We have this hyperspectral remote sensing for that, and also there are multispectral remote sensing. There are different indices are there, or there are enhanced interpretation is there. We can discuss later if time permits. But broadly, we have discussed what are the major rock types, what are the landforms we can interpret, and the geological structures. Now, after this optical region of the electromagnetic spectrum, we discussed particularly visible near infrared, short of infrared. This is the region what in the optical region we discussed. Then we will discuss briefly about the thermal, this part of the spectrum. Thermal, you see, is very, very important for geological applications, because geologically, the most abundant rock samples are basically silicates, isn't it? And silicates have the characteristic absorption peaks in the thermal region. Okay. Anyway, that we can discuss later. Now, see here, the wavelength region 3 to 35 is popularly known as the thermal infrared region. Out of that, in atmosphere, there are the windows are there 8 to 14. 3 to 5 and 70 to 25. Okay, but 70 to 25, this transmittance is very, very subdued, very low. Okay, so this prominent your atmospheric transmittance is available 8 to 14. So 8 to 14 is more popularly used for thermal sensing of the Earth's surface. There is another reason. The ambient this temperature of the Earth is approximately 25 degrees Celsius. At that particular temperature, the maximum radiation takes place close to 10 micrometer. And you see, if you can work 8 to 14, 10 micrometer is in between. So you can sense the Earth's surface well. Okay, if the maximum radiation peak lies in the region of your study, in the spectral region of your study. Whereas 3 to 5 micrometer is generally used for high temperature object detection. Okay. And 17 to 25 is relatively low temperature, but here atmospheric transmittance is very, very low, so it is not used much. But in 8 to 14, if you use a satellite, then at a 9 to 10 micrometer, there is the ozone band that absorbs the most of the radiation. So 9 to 10 we cannot use. So other than 9 to 10, 8 to 14 micrometer we can use for thermal sensing. Generally we use 10.5 to 12.5. Okay. In 3 to 5, there are some solar reflectance contaminants, so that is why it is less used. Okay. Now coming to this, your Planck's law. So Planck's law, this is very, very important for thermal remote sensing. Why, you see, the radiant energy is a function of kinetic temperature of the material and the wavelength of radiation. That Planck has given this relationship between these three. What is these three variables? What is the temperature of the object? What are the radiation, particularly the maximum radiation peak? And what is the wavelength where the maximum radiation takes place? So L lambda is the radiation at that particular wavelength region. Lambda is the maximum radiation peak wavelength, and T is the temperature. So rest all are either known to us. There's pi, like H, there is a Planck's constant, C, the speed of electromagnetic radiation, or the K, the Boltzmann constant. So this is the relationship. It's very, very important. So if you can sense from the satellite, from the aircraft, how much thermal radiation happens, if you can receive that, and if you know the wavelength where the maximum radiation takes place, if you know, then you can easily get this temperature by this relationship. Okay. So now coming to for thermal sensing, what are the these your physical parameters are important, like thermal conductivity, like density of the material, thermal capacity, thermal diffusivity, and thermal inertia. You see, thermal inertia is very, very sensitive. And that is the reason why thermal inertia is very much used for this your thermal sensing of the earth materials. And what is thermal inertia? This is this inertia, resistance to temperature change, given the supply of heat or extraction of heat, supply of heat. It's related to Earth's surface when the supply of heat happens during the daytime, when there is the sun. The supply of heat during the daytime, and during the night, no supply of heat. So radiation of heat from the objects, isn't it? So due to the supply of heat and due to the radiation of heat in the night, okay, how this material reacts, how the material resists to temperature change. During daytime, what is the temperature? During nighttime, what is the temperature? What is the resistance? So how much energy is received from the sun? So total energy minus how much is reflected back? 1 minus A if we do. So this is the energy what is transmitted through the material or absorbed. The solar heat which is absorbed by the material, that is only responsible for temperature change. But now, depending on the material characteristics, thermal inertia property, this material temperature change can be high, can be low. That is characteristics of the material. So 1 minus A by delta T, whatever the value we get, that basically represents the thermal inertia. But it is not the actual thermal inertia. Actual thermal inertia is square root of K rho C. K is thermal conductivity, rho is density, and C is specific heat. And here this is also thermal inertia, but this is not the actual one, but very close to that, and it is known as the apparent thermal inertia. And you see this apparent thermal inertia, that depends on some of the parameters of some of the properties of the material. What are the particle size of the material? What is the degree of induration or compactness? And what is the density and color of the material? Color, this dictates this how much the solar radiation is reflected and how much it is absorbed. The rest all are the inherent property of the material, and it gives the material the resistance to temperature change. For example, if the material is coarse grained, if it is very hard, compact, density is very high density, then its thermal inertia is this is high, and the temperature change during daytime and nighttime will be less. Whereas where the thermal inertia is low or very low, the temperature change will also be very high. During daytime, temperature will be high. During nighttime, temperature will be low due to the radiation. And incidentally, in case of rocks and soil, okay, compared to other things, you can see this plot here. In case of rocks and soil, this is the thermal, this your temperature change during nighttime is high temperature, and during daytime, this is high temperature, and nighttime, this temperature is very, very low. Isn't it? Nighttime temperature is here, and daytime temperature is very high. Very difference is too large. Whereas in the case of water bodies, in the case of damp terrain, again water or metallic objects, this your thermal inertia is very, very high. And because inertia is very high, temperature change is very, very low. Now using this thermal inertia property, we can characterize the material. Now you see this thermal image, and this is the daytime visible image of a particular area, and this is the daytime thermal image. But you see, due to the thermal inertia, water bodies, they have high thermal inertia, no? So temperature change is very, very less. Whereas rocks and soils, their thermal inertia is low, so temperature change day to night is changing more. During day, there are higher temperature, night is lower temperature. That is why water bodies, during night time, they appear bright, means their temperature is relatively higher than the surroundings. Now here you see, this is the topographic slope. This one of the slope segment is sloping towards the sun. So there are more reflection. As more reflection means reflected energy is more. Then absorbed energy will be definitely less, because total energy, it is partitioned. Some energy reflected, some is absorbed. So if the reflected energy is more, then the absorbed energy will be less. If the absorbed energy is less, then the temperature will be also less. So it looks dark. So daytime thermal image, this slope looks dark, but visible image looks bright. So for thermal sensing of the Earth's surface, daytime is not good, because there you will get the differential topographic heating. Topographic effect will be very, very prominent. So for that purpose, we should have thermal image during night time. Particularly pre-dawn is very good, because all the radiation will be over and differential heating effect will be nullified. Okay, so that is the reason pre-dawn thermal image is ideal for the thermal sensing of the Earth's surface, geological materials. Now you see, depending on the thermal inertia, how different kind of landforms have different temperature. Some landforms showing this red color, some are blue color. See, this is a multispectral thermal image. Multispectral means there are different bands. Okay, from 8 to 12 micrometer. One band is near to 8, one is in between around 11, another is close to 12. So different wavelength. Different wavelength is sensitive to different temperature. High temperature will have maximum radiation in shorter wavelength. Low temperature will have maximum radiation in the longer wavelength. That is the reason, depending on the thermal inertia of the material, during the night time, this landform, okay, some landforms will have lower temperature during night time, and some landform, because thermal inertia is high, like compact rocks, hills are there. Their thermal inertia is high, so their temperature is relatively more or less same during the day and night. So nighttime temperature also relatively high, whereas this alluvium, their thermal inertia is very low, so their nighttime temperature is very, very low compared to daytime. So that is the reason you get different colors in multispectral thermal image, isn't it? It is not only the optical image, but in thermal image also you can get the color of the object. Similarly, in case of lava flows, because different lava flows have different temperature depending on when this lava was erupted. Okay, so these older lava flows have the colder. There are the soil formation, there are the vegetation growth, whereas the fresh lava flow, recent lava flow is still hot, no vegetation, no soil. So depending on that, thermal inertia is different, and their color is also different in multispectral image. Now coming to a microwave, okay, radar remote sensing. So here you see, here in case of optical, we use the micrometer range wavelength, isn't it? Whereas in case of microwave, we use a millimeter to meter 1 millimeter to 1 meter is the wavelength range of microwave. But in case of radar, that is the active microwave sensor, particularly in case of synthetic aperture radar, this wavelength is used 1 centimeter to 70 centimeter. Microwave is 1 millimeter to 1 meter, but in case of synthetic aperture radar, it is in centimeter range. So wavelength is very long, almost 10 to the power 4 times than the optical or thermal remote sensing. Because of that, there are some differences in their properties. There are some advantages and there are some disadvantages. Okay, that is also because of its geometry. You see, it is an active sensor. It cannot look vertically down. It cannot be nadir looking. It has to be side looking, up nadir. So red color is a transmitted radar pulse, and yellow are the return radar pulse. So one transmitted pulse give you many return pulse. Isn't it? So you see, because of this your radar imaging geometry and because of the longer wavelength, it has certain advantage. Because it is active, it operates both day and night time. Useful for polar regions. It penetrates through clouds and through rain, and also penetrates through vegetation and ground. So subsurface information up to few meters you can have. Similarly, on the other hand, there are some disadvantage, like it has a granularity effect, like saltpeter image. Image looks like saltpeter, dark and bright, dark, bright like this. So this is known as speckle effect. There are geometric distortion, different kind of geometric distortion like foreshortening, layover, radar shadow. Image is not very this your upright kind of this your object on the image. Radar shadow, sometimes you don't have any information at all when the radar plug does not reach on the opposite slope. Okay, so these are the distortions, and it is not sensitive to color at all and the mineralogical composition. It only depends on the electrical property of the material, particularly dielectric property of the material, isn't it? And the surface roughness. Okay. Now see, radar has certain these your properties. Because of that, it is much more useful in geological studies. Okay, I mean it is not better than optical or better than thermal. It is not like that. So optical has a lot of advantages. Thermal has certain these your applications. Similarly, microwave and radar has certain unique areas of applications. But all together, it is something more. Okay, a lot more. So what are the properties in case of radar, microwave radar remote sensing? It's sensitive to surface geometry because of its side-looking geometry itself. So it provides more information or better information about geomorphology and geological structures. Very sensitive to surface roughness. So it is gives enhanced information about the lithology, particularly in terms of the your grain size or in terms of the the surface roughness of the rocks. Sensitive to moisture content, particularly useful for the unconsolidated materials and soils like alluvium, hydrated rocks, altered minerals like gossans, and also it has the capability to penetrate through vegetation and ground. So it gives information about the terrain in a forested area. Also subsurface geological features like your buried paleochannels, active faults in alluvial terrain. Okay, and sometimes underground civil structures like water or oil pipelines, sewage lines, etc., etc. Isn't it? So see how these images look like. This is an optical, this your brightness image that I have converted a multispectral to black and white image. Okay, the same area you see this your radar image. Okay, radar image of different resolution. See here this Himalayan terrain, it looks so much distorted, isn't it? But here it is upright geometry, you can see. At the same time, you can see the microtopography is very clear here. So geomorphology is much more enhanced. Here you see there is the small this your residual hill, which is so prominent microtopography. But here nothing much is visible here, isn't it? Like here the Shillong plateau, you see, this is the plateau top and the plateau, this your fringe. Here the radar looks from this side, but the opposite side there are shadow. Okay, there are differences. Similarly, here you see this is the Cheria coalfield area. Surface roughness is so prominent. So geological structures you can interpret well. Okay, that is the Southern Modern Fault, and there are some sandstone, carved sandstone bands. These are basically the bending faults. And see how the rock types can be interpreted based on their surface toughness. Okay, limestone, sandstone, and shale can be well differentiated here. And when you merge this radar image with optical image, you have both. You have the multispectral information, so spectral information of the rocks and minerals, because in the optical region, it is sensitive to color and the composition of the mineralogical composition. And radar, it gives you better information about the surface roughness, surface geometry. So geomorphology is highlighted along with their this composition, isn't it? You see buried channel is highlighted. See here there are some landforms. This is the longitudinal dunes. These longitudinal dunes are very much highlighted here because the radar image is merged with the optical multispectral image. Similarly, in the radar image, can be different polarizations. Some polarizations are sensitive to the surface. This information is in a mining area like these overburden dams. There are the settlements, isn't it? So those kind of information will be prominent. Okay, in case of your like polarization like HH or VV, this is HH image. But in case of HB cross polarization, the subsurface informations are highlighted, but surface information no. So see here, subsurface faults is highlighted. Here it is not so prominent. Here you see surface information like the bridge over the river is very, very prominent, but here it is vanished. But both the images are acquired at the same time from the same satellite, RISat-1, radar imaging satellite 1 from the ISRO satellite. It was acquired at the same time. One is HH polarization image, another is HB polarization image. Now coming to briefly about some of the applications. So to begin with, this groundwater related applications. The first is groundwater prospecting or groundwater targeting, where groundwater availability is high, where groundwater availability is not there. Okay, and qualitatively we can say that here groundwater available shallow surface or huge groundwater may be available, and somewhere we can say that limited groundwater available. So those kind of things you can do. Hydro geomorphological mapping is also known as hydromorphogeological mapping. Okay, so here what you need the basic information of geomorphology. You need the basic information about the rock types. Sometimes it may be only alluvium, and some areas like hard rock terrain, geological structures are very, very important. You can have also information about the recharge estimation. Then some advanced applications like aquifer compaction modeling, numerical groundwater flow modeling, then the quality assessment, okay, groundwater pollution hazards. So all kinds of things we can do. Here you can see the groundwater prospect map of National Capital Region, 1:50,000 scale. And here you see this is by our students. They have produced this kind of products. See groundwater prospect and groundwater quality combined together for the Delhi region. So you can understand both. You can get both the information, whether groundwater availability is high and what is the quality of the groundwater. Then here groundwater flow modeling you can do in the Doon Valley. This we can understand how the groundwater flows underneath. Then the other applications like mineral exploration. Minerals can be exposed to the surface, like there are certain minerals, maybe metals and non-metals. Those are exposed to the surface, like bauxite deposits, isn't it? So here, by using this hyperspectral remote sensing, by identifying the spectral absorption peak of the mineral, we can prospect that here the mineral is available. Okay, so mineral deposits can be identified. This is how it is done here from hyperspectral remote sensing. So this is in-member selection, and then this is the mapping. Okay, mapping of this false color composite, laterite bauxite, red soil, and vegetation. So like this, a broad classification, but individual mineral you can identify. Similarly, predictive modeling of the mineral deposits, like base metal exploration of Rajasthan. So here we use many information, like what is the geomorphology, geological structures, and then the geophysical information. Okay, so there are many kinds of this, your geological, geophysical, sometimes geochemical as well. Okay, optical, thermal. In this case, both optical and thermal were used. Then we integrate and we can understand where the mineral deposit occurs subsurface. okay, by predictive modeling approach. And like a GIS, we can develop about the mineral deposits like Mineral Resources Information System, MRIS. Okay, this is just a prototype that can be extended to for the entire country. This information system, different your mining agencies, they have their own mineral resource information system. Okay, nowadays they are doing it. You see, the electromagnetic spectral regions are important for identifying a particular mineral. Like in case of visible and near infrared, this 0.4 to 0.7 and 0.7 to 1.5 micrometer, they are important for identifying ferrous and ferric iron in this 0.4 to 0.7 and this manganese copper nickel in this region. At a short wave infrared, like 1.5 to 1.8, that is SWIR 1, and SWIR 2, short wave infrared 2 to 2.4. These are important for hydroxyl ions and carbonates. Now the thermal infrared region, like 3 to 5 and 8 to 14 micrometer. These are good for silicates and carbonates. Okay, so different regions for different. But what is important that this mineral absorption peak is not very wide, and multispectral bands are wide band. So absorption peak are very narrow, but in multispectral bands are very wide, so it cannot detect this absorption peak. So different others mineral absorption peak can be combined together. So that is the reason you need this absorption peaks is compatible to that you need the spectral bands. Very narrow spectral bands and continuous spectra. So continuous spectra with narrow spectral bands that is available in case of hyperspectral remote sensing. And there are many bands, more than 200 bands, and these bands are very narrow. Okay. So that is very, very important. That is known as hyperspectral data cube. So it is important for identifying the individual minerals, as I told you at the beginning. Now see, this remote sensing is also very, very important reconnaissance tool for hydrocarbon exploration, particularly oil and gas. First is the geomorphic anomaly we look for. Like here you see geomorphic anomaly, you can see drainage anomaly, circular drainage anomaly. It is indicative of subsurface folds. Now, what is the geometry of the folds? For that purpose, we need to go for geophysics, like seismic profile. So here we did the seismic profile, not us. It is done by ONGC, and it is interpreted. They have identified this is this is top of your producing horizon, and there are the number of faults. These are black lines, and this is their interpretation. You see how this folded structure is there underneath. Okay? This is the antiformal faults, and there are a number of faults are there, isn't it? That you can see the profile. Now here it is the prospective areas of the oil and gas. Then what is required? You need to go for drilling and you confirm it whether it is there, and then the production. But here, if there is oil seepage happens to the surface or it contaminates the soil, then some of the absorption peak is very, very important. Hydrocarbons in general, they have the absorption peak in this region, 3.57 micrometer to 3.03 micrometer. It depends on this carbon hydrogen stretching vibrations. When the bonds are steeper, means double bond, triple bond. So that vibrate higher frequencies, means shorter wavelength. Isn't it? But these are all in thermal region, 3.5, 3.03. Isn't it? But they have some secondary absorption peak in 1.73 or so and 2.1. So 1.73 band has been used, and for the purpose of identifying hydrocarbon seepage or the hydrocarbon oil contaminated soil identification. You see, there is an index has been developed that is known as hydrocarbon index. It is developed based on their reflection at these two banks of this absorption peak and this floor of the absorption peak. But the reflection here, here, and their corresponding wavelength, lambda A, lambda B, lambda C, reflectance A, RA, RB, RC, and then this formula. You get hydrocarbon index. If this hydrocarbon index value is high, much higher than 0, then you can say there are substantial this oil seepage has taken, soil is contaminated with oil, or there is a fresh oil is available as the seepage. But if the value is close to 0, very low value, this is the background value. There is no hydrocarbon or oil seepage. Now coming to the geological hazards. So see, geological hazards, I told you earlier. So broadly we call it natural hazards. And in natural hazards, there are three types of natural hazards. And geological hazards is the most important natural hazards. So how we define geological hazards? Naturally occurring and anthropogenically induced hazards of geological origin. These are known as the geological hazards. See, there are three types of natural hazards: the geological hazards, hydrometeorological hazards, and environmental or climatological hazards or climatic hazards. Now, under the geological hazards, we can have internal and external geological hazards. External means exogenous. These are governed by the gravity, force of gravity. So mass movement like landslide, avalanches, rock falls, sometimes riverbed erosion, rock cutting, these are all exogenous. And endogenous, earthquake, volcanic eruption, tsunamis, these are all endogenous geological hazards. Now there can be anthropogenic origin, like mining hazards, like coal fire, like mine subsidence, roof collapse, isn't it? And urban hazards, like groundwater depletion, aquifer compaction, land subsidence, then water, this year pollution, okay, what contamination with the arsenic or the fluoride, high concentration of fluoride or arsenic. So these are dangerous. Now see landslide, the active landslide, you see this is the ground photograph and on the image how it looks. So this is the scar, isn't it? The scar over the image is very, very clear. Why? Because the area was previously, before the landslide, there was vegetation covered. But because of the landslide, all the vegetation was with the rocks are slided down and this trace rock exposed. Okay, so it looks like this. Now you see in case of Uttarkashi Brahmavat landslide, before that there was no scar like this. In 2000, there was no scar. In 2001, this Brahmavat landslide happened and this trident-like scar developed. And then after that, there are many times the landslide has been rejuvenated. Many times the landslide has happened, recurrent these activities of landslide. And here we have worked in this particular area. Even before the landslide, the Bornavat landslide, we have identified as a high hazard. In 2000, this map was produced, and 2001, there are the big landslides happen. And again, we have worked for that in a higher resolution. Okay, here we have used 1:50,000 to 1:25,000. Now we did it 1:10,000 scale or even higher resolution. Okay, that is important to pinpoint which area is more is affected, and which area is not going to be affected. Now coming to the seismic hazards like earthquake, you see recently in Nepal there was a big earthquake happened. 7.8 magnitude earthquake occurred 80 kilometers northwest of Kathmandu city. Kathmandu city is here, and here is this focus of the earthquake. Okay, so 25th April, Gorkha is the name of the village. And this again, there are a lot of aftershocks. These are all the gray dots are aftershocks, and some of them are above 6. And one of them that occurred in 12th May, that is 140 kilometers from this main shock from here. Okay, this is the main shock, and this is the 140 kilometers far. There, this aftershock is 7.3 magnitude at Kodari village. Okay, this is shown here. This is the main shock, and this is the aftershock. Now you see there are technology using this your microwave SAR data and the data processing techniques is known as interferometric SAR technique. So use two images, one image before the earthquake, another image after the earthquake, and then process their phase difference by the technique of radar interferometry. So you need two images and interferometric processing. We get the differential interferograph after compensating the topography. And we find this is the displacement of the Earth surface due to the earthquake. And you see these are each color cycle represents 25 centimeters. And you can count the color cycles. And this area is uplifted. You know how much upliftment happened? 165 centimeters along the radar line of sight, 165 centimeters. And this area subsided along the radar line of sight. So this area subsided 60 centimeters. And this aftershock is less affected, but not so less. Here the uplift 65 centimeter and the subsidence is smaller area than this main shock, because the magnitude was much smaller. And this is subsidence happened here 35 centimeter and uplift 65 centimeter. And if you take the total this effect from before the main shock to after the major aftershock, this total effect looks like this. Similarly, these anthropogenic hazards like mine fire. See, this is the Jharia coalfield. This is there are 54 Gandhara coalfields in India, and Jharia coalfield is one of the most important coalfield in terms of the coal resources, quality of the coal, and also damage. How much this your coal fire is there? There are the subsidence is happening, roof collapse is happened particularly earlier. Now it is much reduced. Okay. Now see, this is the open cast mines. So we have large number of studies we have about this area, and there are many more groups have studied. And this is the fire. This your field photographs. We have studied from the early 90s to the 20s. See what is the situation of the coal fire. Sometimes it has reduced in 2009 or so, but again increased. So we have all these monitored map. How much is the surface coal fire? How much is the subsurface coal fire? What is the surface coal fire? Very precisely, you can identify using Schweerback data. That should be night timing. And then you can have a complete mine plan, environmental indicators, like where is the overburden dumps, where are the coal dumps, where are the open cast quarry, where are the surface fire, where are the subsurface fire, all these things you can have. As well as where are the land subsidence happened due to underground mining, particularly old workings. That underground mining occurred much before nationalization, but old working remains, and it got waterlogged, and coal fire also migrated to those areas, and it makes this area void. The coal has been burnt out, and that subsidence happened, isn't it? So we use the C band and L band SAR and interferometric SAR technique and identify these areas that is subsiding, not collapse, subsiding. But its rate is not so less. Sometimes rate is, you can see here 30 centimeter per year, or even up to 50, 55 centimeter per year. But depends on this where the area is located. Above the old working, the subsidence is more. Or there mining is done by caving operations. Subsidence sometimes it reaches up to 1 meter or even more per year. So we have identified this area which is at this moment subsiding when the study was done some years back. And again, we compared with the ground-based survey. We prepared this your affected area. This is the subsiding areas or coal fire areas we have mapped using the ground survey, total station and ground-based survey. Then we compared some of the areas we find these areas we have mapped, which is not identified here because it is only this your ground survey was done only in and around the presently mining area. Old mining area, no, not much important by the mining agencies. But here we see the entire area. You can see this is what kind of this cracks developed, what kind of subsidence happened. Then in case of this urban area, particularly many of the cities, the groundwater extraction rate is very high, much higher than the groundwater recharge rate. And the aquifer becomes empty. Because of that, this aquifer as well as the confining layer above the aquifer, there are this water leakage happened from the confining layer. So this compaction of the aquifer system happens. I'm sorry. And this land subsidence. So this land subsidence we can identify from using this technique, interferometric SAR technique. You see, this is the groundwater depletion area. This is not subsidence, the groundwater depletion area that we have mapped from the central groundwater board data. See, these are the areas where the ground depletion is very high. Ambala, this is the Mohali, Landran, and this area, then Kurali area. This area where ground depletion is very high. Similarly, when we see in case of radar interferometry, similar areas are affected. Mohali, Chandigarh. Chandigarh is much less. Mohali, then Kharar, then Panchkula, then here Banur, and this below is the Ambala. Here is the Ambala also. So these are the areas where subsidence is happening. You can see. And the rate of subsidence, you see, it exceeds 10 centimeter per year, almost 10 centimeter or more. particularly in case of Mohali and this London, this area, Kharar area. Okay. So this is Kharar and this is the Mohali area. And there are Ambala city also. But due to that, to find many of the buildings, there are the cracks developed, building cracks. And these cracks, we have studied the characteristic of the cracks. What kind of cracks have developed? What are the stress pattern? Whether the tensile stress is responsible or the compressive stress or shear stress. What kind of cracks are they? Tensional cracks, then vertical cracks, or horizontal cracks. With this tensional, it can be horizontal, it can be vertical. This is compressional cracks. Okay. This is the tensional vertical cracks. You can see this. If tensional, then this your crack will be opening will be more. With compressional, crack opening will not be there. The mounts will be developed near the crack. Okay. Well, there may be shear crack as well. So these characteristics of the cracks. But generally, this happens mostly in case of masonry building. If this building structure is well structured at CC, then this damage is very, very insignificant, very less. In general, most of the damages occurred where the building, the structure is not good. Okay. With this, I will conclude. And before that, you see, not only remote sensing, but you need to take a lot of measurements by the ground-based instruments. Like if it is a mineral, then you should go for this spectroradiometer. Like in optical region spectroradiometer, we have ASD spectroradiometer or FTIR that works in the silicate rate. Mineral for the silicon minerals, thermal spectra. Like it is from 3 to 16 micrometer, or 3 to 16 micrometer range. So from this is up to optical region, 0.4 to 3 micrometer. Similarly, if it is engineering geological properties of the material or geotechnical properties, then we need to go for engineering geological properties, like direct shear this test instrument. We have engineering geology lab. And geophysical instruments are very, very important to see what is subsurface, like ground penetrating radar or GNSS is very, very important, you know, that is the positioning and how far the earth crust is under deformation or it is this movement is happening. And there are instruments like total station, there are resistivity that can sense the aquifer at what depth, or this you're mapping this buried paleo channel. Okay, with this I conclude. So if you have any questions, you can write to me either of these two emails. This is Gmail, rscirs@gmail.com, or this is this IRS email address. Okay, so with this, thank you. I conclude my talk. So I believe we have many queries, many questions. I'll see what are the questions you have, and I'll try to answer to that, or we'll discuss on them questions. So for that, in between, we'll have few minutes break. Okay. After that, we'll discuss. We'll come to the question answer session for another few minutes. Thank you. And thermal region is important in some of the areas where the thermal anomaly is important, particularly in case of coal mines, isn't it? And the microwave is important for identifying certain features. Those are not cannot be mapped in case of optical vision. There are problems, and advanced techniques like sometimes interferometrics are, sometimes polarimetrics are. These are important for that. And then all this information, what you gather from different kind of this your data and different kind of techniques. So this information you need to combine together in a GIS platform, and you need to integrate. There is one question is okay, topographic and geological data. That question is there. So I'll discuss later. So whether applications show wrong info when it shows rain on a time, but that time it might be sunny time, and also with that day high rain. Yeah, there will be effect of the rain. But if you use microwave, so this kind of effect will be minimized. Okay, particularly in case of standard radar image, you won't find any effect in microwave. But see, surface properties will change. So when there is rain, the surface will get wet, and so this dielectric property will change. So you definitely will get the different kind of signatures. So now this third question is explain the process of integrating topographic and geological data using GIS and hydrological for hydrological mapping. So mapping hydrogeological, maybe anything. So that application you have to use later depending on what kind of information you need. This is hydrogeology, isn't it? Hydrogeology means aquifer properties you want to know, isn't it? And mostly hydrogeological properties means that is what kind of this your these hydrogeological properties means what is the porosity, permeability, and what is the extension of this. Okay, so now your question is how to integrate topography and geological data. So topographic information like elevation data, isn't it? So if you have the topographic elevation data, and if you have the geological map, so you can integrate together. Okay. So you can integrate by number of categories. You can go by this your like your color transform, by the statistical integration like principal component transform, okay, or the IHS transform, or by multiplicative techniques, or there are some these advanced techniques like wavelet. Okay, so you can merge these two data. Now, what information is important for hydrogeology? Where to understand the aquifer properties, aquifer geometry, then you have to use accordingly. Okay. So it is a little tricky. So maybe uh, it is not completely clear to you. But first, merge these two products and find out what is the combined product. And this combined product, how it is helpful to hydrogeological mapping. Hydrogeological mapping means you need to identify this. What is the elevation? Is similar kind of elevation, whether the water table properties you can understand, isn't it? If the particularly this your water table is follows the what is the topographic this elevation pattern or topographic slope in case of particularly alluvial terrain, isn't it? Now, see, next question we are coming. How do we understand how to filter the numerous bands in the hyperspectral imagery to achieve the desired image? Since there are so many. Okay, so filtering first you see. First, you have to filter out the noise. That is the first filtering. So first filter out the noise. Okay. After that, you can use all the bands. That is not an issue. What you need to see that you have to have some kind of spectral mapping, and then you find out the end members and then compare with that what you want. So they compare the mineral spectra and what the spectra you have, then you can do that. Or if you want to do manually, then you have to see the where your mineral spectra lies. So in and around that, these bands you can use. But you don't need to do that. Okay. You only identify the end members. And then depending on the end members with the mineral, what you want to target, and you compare the spectra, and then you can do that. Accordingly, you can select this end member and map it accordingly. Okay. Now this Mr. Arvind has asked how satellite imagery used to detect geological hazards such as landslide. See, this is a little general question. So landslide means landslide can be of different types. I have not discussed at depth. So whether landslide is a fresh landslide, as I have shown, there are the scar will be visible. So scar mapping is very, very easy. You can take one image before, one image after the this landslide happened, and very easily you can map the active landslide or landslide scars. But old landslide, for that purpose, you need to use the topography as well and the material type. I mean, geomorphology you have to use. So where the slope changes is less, gentle slope, loose materials, vegetation growth, we can identify this is this potential areas of old landslide in the mountainous areas. Okay. Now earthquake hazards, you see seismic hazards. This you can very easily by change detection you can do, but for seismic hazard, potential seismic hazard, that is a different thing. It is not the before and after. So before and after you can see what are the changes, what are the damages happen, and what are the liquefaction hazard also you can map. But what is more important, that potential seismic hazard, before the earthquake happens, you can tell which area is more prone to damage, depending on where the earthquake prone areas. Depending on that, what would be the PGA, considering the in situ conditions, material conditions, what are the material type, whether a loose, unconstituted material or hard, compact material, what are the geomorphology, okay, whether it is undulated or not, whether there are the ridges or valleys, or the area is flat mostly. Depending on that, PGA will be different, peak ground acceleration, and also liquefaction hazard you can do, because liquefaction is nothing but it is due to shaking of your uh, loose the particles like sandy or silty particles. If there is water and due to the shaking, it will make this like of this your what should I say, material which can flow, viscous material, and it can flow underneath and the buildings will be collapsed. That is liquefaction hazard. So those kinds of potential hazards you can have. We have number of these research papers are there to how to do such studies. Okay. So this is okay. There are very few questions, Ashokji. No? Only. So
yes,
there
sir.
is no more questions. Okay, good.
Yes.
So, okay, then I can conclude because there is no question.
Yes, sir.
Okay, thank you.